Alright, this is notes over a new chi-square test called the Homogeneity of Proportions. And in a goodness of fit test, we're analyzing the distribution of one variable in one population. In a homogeneity of proportions test, we're analyzing the distribution of one variable in two or more populations or treatments, where the variable can have two or more categories. So just to kind of compare the two, for example, if I wanted to know if East High students prefer a particular subject, math, etc., we would do a goodness of fit test. And I would go around and I would get a bunch of observed values for the different subjects. So math, science, and English. Okay, I'd get a bunch of observed values and I'd have a total. And I would have one observation under each one. That would be a goodness of fit test. Okay. Today we're learning a new test that says, well, let's say I want to do the same thing, but I want to see if girls prefer different subjects than boys. So I would do what's called a homogeneity of proportions test, in which case my table becomes bigger. It becomes a two-way table. So I would still have my math, my science, and my English columns. Okay, but this time I would have columns for what the boys like and what the girls like. And then I would have a total for each one. So then I'd have a total here and a total here. Alright, so basically this is like we've had tables like this way back in chapters 3 and 4. This is called a two-way table. Things that are going this way are called rows, and things that go down are called columns. This would be the total of the boys. This would be the total of the girls. Down here's the total for math, total for science, total for English. This is the grand total right there. So the test statistic is the same. We're still going to have observed values. All of our observed values will be found in here, and we'll be able to calculate expected values. Now the expected values we'll learn to calculate it a little bit different way. Okay, so the expected values are different, and calculating the degrees of freedom is different. But otherwise it's the same test. So suppose that independent random samples were taken of voters from 4 different regions of the country, and that each voter's political affiliation was noted. Are political party affiliations the same throughout the U.S.? So we've got this table here, and I guess what I would notice is that there seems to be a lot more Republicans in the South and Midwest than there are in the Northeast and West, and there's a lot more Democrats in the Northeast and West than there are in the Midwest. So I guess I just noticed, to me, they appear to be different. Now the question is, why would I want to combine all of the other political parties into one other category? Well, this has to do with checking the conditions. All right, your conditions, the expected counts, all have to be greater than 5. And so that by combining those other political parties into just other, then we really don't have to worry about that as much. So in this example, what are the populations and what is the variable? So the populations are the different regions of the country, because they want to know if political party affiliations are the same throughout the U.S. So the variable that we care about is the political party affiliation. So the variable is the party affiliations, and the populations are the regions of the country. And this is important that you can differentiate between the populations and the variable when we talk about independence later on. Alright, so to find the expected counts, we must assume the null hypothesis is true. Alright, the null hypothesis would be, in this case, that the party affiliations are the same across the U.S. The alternative is that they're not the same throughout the U.S. In other words, where you live could determine which political party you associate with. All right, so what we want to do is we want to find the expected counts. Okay, we want to find the expected counts here. So finding the expected counts, well, we have our totals. Our totals are going to guide our expected counts. So we're going to use our totals, use the row totals. These are row totals. And the column totals. These are the column totals. And the grand total to figure it out. All right, so on the top of the next page, they kind of guide us through this. And then we'll fill that out. So since Republicans make up 0.429 of the overall population, well, where did that come from? If I take 458, the number of Republicans, okay, if I take 458, the number of Republicans, divided by 1,067, they're getting the numbers on this next page from here. In fact, let me tear this off, and I'll just put this right up here so we can see it. There we go. All right, so since Republicans make up 0.429 or 458 over 1,067, then according to the null hypothesis, the Republicans should make up 0.429 of each region. So all you're going to do is basically going to take each region total times 0.429. So 266 times 0.429, 272 times 0.429, and the other totals times 0.429. All right, now since Democrats make up 0.442 of the overall population, or 472 over 1,067, then according to the null, the Democrats should make up 0.442 of each region. So we just are going to take each region total times 0.442. Each region total times 0.442. Now, how would I get that last group? Well, if I have these two values, if I have this and this, I can add these together and take it away from 266 to get that one. These three better add up to be 266. So a formula for the expected cell count, which is really easy, is the row total times the column total divided by the grand total. The row total times the column total divided by the grand total. So in other words, if you look up here to find this value, I'm going to take 266 times 458 and divide it by 1,067. Okay, that's really what we did up here. We divided these two and then took it times this. So it's the row total times the column total divided by the grand total. So I could get this value by taking 266 times 472 and dividing it by 1,067. I could get this value by taking 267 times 472 and dividing it by 1,076. Now with these, you're going to round them, usually to the nearest whole number is fine. If you wanted to use tenths, that's okay, but since there's so many values, it's usually easiest to round them to the nearest whole number. So that's what I did here. So I have the filled out one. Right here. So these are all of the expected counts, and this is something that you have to make sure you fill in for your conditions. So here's basically the whole hypothesis test right here for this problem. At first glance, it appears that political affiliations are not the same throughout the country, since the observed counts are different than the expected counts. It is possible that the political affiliations are the same, and we got these differences due to sampling variability. To decide, I will conduct a chi-squared homogeneity of proportions test. That's the name of our new test today. The null hypothesis is political affiliations are the same throughout the country, and the alternative is that they are not. Okay, same type of hypotheses that we had before with the chi-square test for goodness of fit. All right, our conditions, was it an independent random sample? Yes, it was. That was given. And if it's an experiment, you have to check if the treatments are randomly assigned. We would assume that 1,067 is definitely less than 10% of the populations, yes. And is it a large sample size? You have to have your expected counts written somewhere. So there's my expected counts, and they are all greater than 5. So you can't just say that, you have to also write down your expected value table. Okay, so now to go through the calculation here, what would you have to do? Well, we would have to take our observed values that we had. So all of our observed values happen to be, not even sure where they went now. Here we go. Here's all of our observed values. Just going to put this right here. So here's all of our observed values. We'd have to take this observed value minus that expected value, and this actually had it. This actually rounded it. So they took 86 minus that, they square it and divide it. So you would have to do that for every individual cell just in here. Each of these are the observed counts. You don't do it for the total counts. These are what you do it for. So they calculated every one of those differences, and we got 66.8. Now I'm going to show you a faster way to do that on the next page. You can do this homogeneity of proportions test on your calculator. All right, so there's my chi-square statistic. The degrees of freedom, the way you calculate degrees of freedom here, degrees of freedom is the row total minus 1 times the column total minus 1. So our row total, our rows, if you look here, we had 3 rows, so 3 minus 1, and 4 columns, 4 minus 1, so 2 times 3 is 6. So that's where we got the degrees of freedom of 6. And the p-value does happen to be 0 if you do the chi-square CDF, and you'll see you don't need to do that on the next page. So our conclusion is we reject the null and conclude that party affiliations are not the same throughout the U.S. So which type of error would we have committed? Could we have committed? It would have, since I rejected the null, it can only be a type 1. I decide that they are not the same, but actually they are. All right, almost done with these notes. Actually, we have one more example that we want to look at. And I'm doing a short version. You should make sure you write out all your steps here, but I just want to show you how to do it on your calculator here. So what we have is we have information on more effective treatment for epilepsy, surgery, or drugs. So if you read through this, it tells you that 15 of 36 patients who had a chunk of their brain removed were free from seizures a year after operation. Only 1 of 40 patients who received the standard drug treatment were free of seizures. Is there a significant difference in the effectiveness of the treatment methods? All right, so there's 2 treatments. One is brain removal, and the other is standard treatment. Okay, so the brain removal, we had 15 out of 36, this will be my total column, that were seizure-free. Okay, so these obviously had seizures still. And for the standard treatment, only 1 out of 40 was free of seizures. So what that leaves me with is here, this will be 21, and this would be 39. All right, I'm going to stop this. I'll have another video to finish this up because I don't want to rush through in a few seconds. So.